11. The actual doing, I'm going to talk about both of these, but the actual doing is experiment 11. So your pre-lab should be for experiment 11, and you're going to be using your product from last week. So keep that in mind when you're preparing your pre-lab too. It needs to reflect the product from last week being used in experiment 11. So it should be individual towards what you made with your Grignard reaction. We'll have a quiz. Your experiment 7 report is due, and that is in your notebook. So you're handing the whole notebook over with the conclusion. Remember, that guy's 75 points, so do a good job writing up that experiment. Next week, we're going to do experiment 12 and 13. The doing in lab is 12, in case you're getting ahead on pre-labs over the weekend or such. So if you want to, before you see me next week, if you want to do the pre-lab for next week, you're going to pre-lab experiment 12. Okay. In 2 weeks, your experiment 8 and 11 report is due. A couple notes with that, because we're now going to put two experiments together in one report. Keep your pre-lab and your experimental for each of these on separate pages. So don't combine experimental and pre-lab for experiment 8 and 11. They should be separate. We'll be writing a common conclusion, because you use the data for one to then look at the data for the other experiment, okay? So pre-lab and experimental are kept separately. The conclusion, you'll write one conclusion for both of those experiments, okay? So be careful of that when you're taking care of things in your notebook this week, because it's really easy to want to put the two of them together. Couple notes for registration for this week for Chem 256 A and B. So I talked about each of those last week. First of all, you need to take A to take B. So I didn't mention that last week. You can't just register for B without taking the A portion. You need the A portion before you take B portion. Sections 1 through 4 will have both A and B offered for those sections, okay? Section 5 is only the A portion, is only the first half of the semester. So if you're registering for section 5, make sure you don't want to do the independent project. That section is only the first half of the semester, not the independent project, okay? Yes?
And we can register for 1 through 4.
Yes. Yeah, and so if you don't want to do the project, you can also register through 1 through 4 as well for the A portion. But if you want to do the project, make sure you're in sections 1 through 4 and not in 5. Okay? So any section you can do the A portion, but for the B portion, you want to make sure you're only in sections 1 through 4. Okay? All right. Couple notes from last week, because you guys are going to need to finish the fractional distillation for experiment 8. So I talked about last week, make sure you know the boiling point of your alcohol before you do that fractional distillation. It should be greater than 100 degrees, okay? So let me give you more information, okay? So 3 heptanol, you should have a boiling point of about 156 degrees. Same with 4 heptanol. And then your octanols, your 3 octanol and your 4 octanol. So in the end, you guys, you only made 4 different, even though you had a bunch of different combinations, you made 4 different alcohols. The 3 and 4 octanols should be about 174 to 176 for their boiling point ranges. So make sure when you're doing that fractional distillation, first of all, you have good thermometer placement to get accurate boiling points, but you don't want to throw things away that are boiling at these temperatures, because that's your excuse me, that's your boiling point of your alcohol, and you're going to collect starting at about 20 degrees below that boiling point, so that you make sure you do get all of your alcohol. Now, after that boiling point range, you probably aren't going to have a whole lot left, so just watch the distillation to make sure you leave a little bit in the all-in-one simple distillation apparatus, so you don't go to dryness, because if you go to dryness, you could potentially have a fire. So just keep an eye on things, okay? You probably, if you start going above these temperatures, then stop the distillation, but also watch the volume, because you may not even get to going above the temperature, okay, before you're out of stuff to distill. So just be careful with those, okay? So then, once you get your alcohol distilled, there's a couple things that we need. We're first of all going to need our yield, and that can be, you can do that kind of two ways. You can do a yield of all the fractions that you are saying alcohol is within them, okay? And then you can also do a yield of what you say is your purest fraction of alcohol as well, okay? You need to collect an IR spectrum of your alcohol, and then you're also going to make a GC sample, and I'm going to talk about here in a little bit how to prepare that, okay? So before you go on to experiment 11, make sure you have figured out your yield, okay? Make sure you've at least set aside a little bit for collecting the IR, and make sure you have prepare your GC sample before you go on to experiment 11, okay? All right, so now for experiment 11, we're going to look at the elimination reaction that'll take place with your alcohol. So I'm going to use 2-heptanol as an example here. Drawing the same thing I'm telling you about. So we are going to react our alcohols in the presence of an acid, and in order to get the elimination reaction, we should see a mechanism of this. And so we're in acid, so we can have a positive charge here. And we're going to lose water after we protonate with the acid, okay? Now in terms of elimination reactions, because we have an intermediate, do you guys know what elimination reaction that is? So it's not a substitution, it's elimination. Have you gotten to your E1s and E2s yet? So it's an E, you're right on the cusp, okay? So it's an E1 reaction because we have an intermediate, okay? And so then what we get is this positively charged species, okay? So we've got this carbocation. And we can form then the double bond to form the alkene a couple of different ways. If we have our electron flow going this direction, so we have conjugate base of our acid taking this proton and then forming the alkene. In this case, we would get 1-heptene. Now, would you have cis and trans 1-heptene? No, right? Because you don't have two different substituents here, right? Okay, so it's just 1-heptene. The other possibility is we have our conjugate base take one of these protons, and then we form our alkene here. So in this case, we get 2-heptene. Now would we have cis and trans this way? Okay? So you would have both possible compounds, okay? Cis and trans 2-heptene, all right? Now, another thing that can happen with this and with the E1 mechanism is we could have a hydride shift too, okay? And so we could always move a hydride to make an at least equally stable carbocation or a more stable carbocation. So if you look at what's going on here, we've got this carbocation. We wouldn't shift to this direction, right? So that we would form a carbocation out here because we've got a primary carbon, or be a primary carbocation. So the only direction we're going to move the hydride is such that we get a more interior carbocation. And so some of you may see some of this happening with some of your products as well. So instead, we move our carbocation in here. Then we can form products. Then we could go either having our 2-heptene form, or we would form our 3-heptene. So keep this in mind as a possibility when you're analyzing the products that you get from GC, okay? But you're not usually going to go, you're fighting energy barriers to go to a less stable carbocation. You're usually going towards an equally stable or a more stable carbocation when you do the hydride shift, okay? Now something else to keep in mind is Zaitsev's rule when we're talking about alkenes. What does that rule say? What are we going to form? So in relation to looking at hydride shifts, the more highly substituted alkene or alkenes are going to be the major isomers, or are the major product. Okay. Now, what about cis and trans? What do you know about cis and trans as far as looking at different products and substitution?
It's more like the trans one, right?
Right, we're going to want trans will be greater usually versus cis, okay? But does that mean you will only form trans product? No, you will still see cis product, okay? So just because you should expect a greater amount of trans product, don't negate that you're not going to have any cis products. You will always have cis product for trans product. So keep that in mind because it gets a little tricky looking at your GC data when you're looking at your alkenes, all right? So cis and trans will be there, usually more trans than cis. Now for this elimination, what we're going to use is sulfuric acid, okay? And so the conjugate base is HSO4 minus. The reason that we do this is a really weak nucleophile, okay? When we get to where we've got the conjugate base out there, if we had a strong nucleophile, what's another possibility for the type of reaction we could have? A substitution reaction. So we want only an elimination reaction. We don't want a substitution reaction, okay? So we use sulfuric acid so that we're forming HSO4 minus versus if we use something like HCl and we form Cl minus, this would cause some substitution products too, okay? So to get just elimination, we're using H2SO4 as our acid. Now be careful, because in order to get this reaction to work, it's not like we can use like 1 molar H2SO4. We've got to use concentrated acid, okay? So we're not using fully concentrated 18 molar, but it is going to be 9 molar, okay? So it's only half dilute, so be really careful handling it. It's the same sulfuric acid you used last week, okay? But last week you ended up diluting it before you worked up your Grignard reaction. This time we're using the 9 molar sulfuric acid, and we're going to heat it we're going to distill with it, all right? So be careful handling that, wear gloves, and make sure you keep it contained. Any spills we have, we want to make sure we get cleaned up right away, okay? So what you're going to use, the type of technique, is going to look very similar to what you've done before, but we're going to use what is called steam distillation. So we're going to use still a steam distillation apparatus, but this time we're using the steam distillation because we're getting the sulfuric acid and the water from the sulfuric acid distilling over with the alkene as it's being formed, okay? So you're basically going to have your alkene and acidic water distilling over at the same time, okay? And so as the reaction is taking place, we're then distilling over the product to hopefully push it to make more product, because we are technically in equilibrium with this reaction, okay? So we need to pull away product as we make it in order to generate more product from the reaction, okay? And so what you should see with this steam distillation is as it comes over, it's probably going to, when it's hot, it's probably going to be mostly one layer that comes over. It's going to be cloudy because it's a mixture of the two things, but you're not going to see a definite difference between the two. But as it cools, you're going to see two layers that form. You'll have your alkene as your organic layer, and then you'll have the acidic aqueous layer, okay? And so what you're going to do is you're going to set up your simple distillation just as you have a number of times now. But you're going to collect the distillate in your 25 milliliter graduated cylinder. Okay? And the reason for that is then you can see and measure how much volume you're making of your alkene versus that water layer. Because what you want to do is distill it until you get as much alkene out as possible, but when you stop collecting organic layer, you want to stop the distillation. Now sometimes what happens is it looks like you've stopped collecting the organic layer, but you don't have really enough aqueous layer to compare it to, so you keep the distillation going just a little bit longer to make sure that that top layer isn't growing and it's only growing into the bottom aqueous layer, okay? But you're not going to, you're starting with 50 milliliters of 9 molar sulfuric acid. You are not distilling all of that over for this experiment. You're just distilling until you stop growing that organic layer. So you're going to stop the distillation once no more organic layer is being collected. Now you're going to collect a similar volume to alcohol that you put in. So you're probably going to get about 2 to 6, 7 milliliters of alkene. It is not going to be a lot of product, and it's going to be sitting in that graduated cylinder. So make sure you secure that graduated cylinder so it doesn't dump over, because if you dump over your product, you've lost the majority of your product and will have to extract it off the surface of your hood so you have something to work with for this experiment. So it's not a pleasant experience, but we have done it before. So I'm now warning you to be careful, okay? Let everything completely cool down before you start taking things apart, because again, you've had boiling 9 molar sulfuric acid. You don't want to take that distillation apart when it's still hot. Let everything stop dripping. Let everything stop get cooled down, stop being hot. The first thing you want to do is secure the graduated cylinder with your product. Make sure that is in a secure place where it won't tip over, okay? And then be careful when you take apart all the pieces. You want to rinse all those pieces out with water to get all the acid out of all your pieces to your distillation apparatus, okay? Now, the distillation pot. So what's left of that 9 molar sulfuric acid, which is probably, you know, either a darkish amber brown or almost a black color by now, okay? You are going to pour, once it is cooled down to room temperature, you're going to pour the contents into a large beaker with about, you know, like about half filled or 2/3 filled with water. Okay? And just carefully pour that into the water. We're diluting that acid, okay? And then you're going to pour the contents of the beaker down the sink. With lots of water. So, does this go anywhere near your organic waste container? No. We do not want acid in the organic waste container, because as you found from experiment 6, a lot of you, especially sulfuric acid, will react with organic compounds. We don't want something that's going to react with organic compounds in the organic waste container, okay? So it's really important to pour it into a large beaker of water once it is cooled completely to room temperature, and then pour it down the sink in your hood with lots of water flushing it down, okay? But do not let it go in the organic waste container, all right? Okay, now with your alkene, we got a couple steps of workup, but we've got to be really careful with it because we don't have a lot of it, okay? So the first thing you're supposed to do is wash it with the 5% sodium bicarbonate solution that you used last week. Okay, so when I say wash, what does that involve? Same as last week. We're going to add the 2 in, shake and vent a few times, let the layers separate, drain the aqueous layer, and then separate out the organic layer, okay? Then you're going to dry your organic layer with meg sulfate. So a lot like you did last week. However, this is going to be a lot less magnesium sulfate that you're going to use. Your alkene is neat. We do not want to add any solvent to it, because if we add solvent to it, then we're going to have to do a simple distillation step to remove that solvent, okay? So you're not going to use a lot of magnesium sulfate to dry it. So be really careful that you add just enough to have some clumping and a little bit free floating. But be really careful because it's such a small volume, it's really easy to make pancake batter out of it instead of just drying it, okay? So be careful, not too much on the magnesium sulfate. We don't want to have to add any solvent to it, all right? Now because it is such a small amount of magnesium sulfate, the only reason you have experiment 9 in your lab manual is for this figure, okay? So here it is. So I guess we could say it's like 9, 10, and 11 this week. You are going to make what's called a filtering pipette to filter the magnesium sulfate because it's that small of an amount. We're not going to use regular gravity filtration with your regular filtration funnel. You're going to put a little teeny piece of Kim wipe in the base of the pipette, and we have little wooden sticks with flags to help you do this, okay? What you don't want to do is use another pipette because then you'll break the pipette off in the other pipette. So don't use another pipette to do this, okay? Put a little teeny piece of Kim wipe in the base of the pipette, and we've got our little wooden sticks to help you push it in there. Now you don't want to pack it so tight that nothing can flow through it, okay? We just want to trap the magnesium sulfate. So just pack it in there, but not as tight as you possibly can, okay? Then what you're going to do is you're going to filter, or pipette, I guess, your alkene into this pipette. So using a different pipette, filter into this pipette, all right? And then you're going to have it all drain into a vial that you know the mass of, okay? Because then you don't have to go and transfer it again in order to get the yield. But this is how you'll gravity filter away that magnesium sulfate, is by going through this filtering pipette to do that, okay? Then the filtering pipettes will have beakers in the hood for these, because the alkenes, just like the alcohols, have some stink to them. So we'll put a beaker in the hood that's just for these pipettes when you are done. So don't stick them in the glass waste, because all the glass waste will stink. What I want you to do with it, though, before you put it in that beaker, is in your hood, when you're all done using it, rinse acetone through it to help get residual alkene out of there. So make sure you're done with it before you do that. And then stick it in the beaker in the reagent hood, and we'll let them air out before we put them in the glass waste container, okay? But just be really careful, because again, we have a tiny amount. It's easy to dump things over, so I'd probably clamp pieces so they don't get dumped over. And then if you know the tear weight of this vial, you can easily get the yield of the alkene, all right? So for the alkene, just like we needed for our alcohol, we'll need the yield, okay? You will need to collect an IR spectrum, and you will need to prepare a GC sample. For both of these, big this week is we have to have the yield. Alcohol, we have to have the yield before you go on to experiment 11, and we have to have the GC sample before you go on to 11. Before you leave this week for experiment 11, we need the yield and the GC sample, okay? The IRs can always be collected in an open lab. So if you're running low on time, yield and GC sample have to happen. IR can happen in open lab, all right? Now, for both your alcohol and your alkene, with the IR, you're going to want to compare it to a literature IR spectrum. So what you want to do is look up what would be the spectrum of your alcohol and what would be the spectrum of a predominant alkene that you are going to make, okay? If you can't find those spectra, then use something that's closely related. So say you made 3 octanol last week with the Grignard reaction. You can't find 3 octanol, but you could find 2 octanol. That is similarly related, versus instead of using 1 octanol to compare it to 3 octanol, okay? At least 2 octanol is still a secondary alcohol, versus 1 octanol would be a primary alcohol, okay? So same with the alkenes. If you can't find the predominant alkene or alkenes you're supposed to make, then find something that's isomerically similarly related to it, okay? Now for your pre-lab for experiment 11, I told you it's based off of the alcohol that you made last week. You have to predict what your alkene products, based on what we've gone through for the formation of the alkene. In your pre-lab, you need to show the reaction of your alcohol. What are going to be the predominant cis and trans products that you're going to make based on that alcohol? So make sure you show those in your pre-lab, okay? All right, questions on 11 before I start on experiment 11. Or sorry, questions on 11 before I start on experiment 10 GC. Okay. So GC, we're going to look at our second chromatography technique. So we already looked at gel permeation chromatography a couple weeks ago. Now we're going to look at gas chromatography. And so both our experiment 8 and experiment 11 products are going to be analyzed with gas chromatography, okay? And more specifically, what we use is what is called capillary GC, and that's because the column that we use is so tiny. So we'll show you guys this column in lab this week. It is really, really, really tiny, and within that column, there's even stuff in the column, so it's an even smaller space that your sample actually passes through, okay? So it's like, kind of similar to the capillary tubes that you use for melting points, but even smaller in diameter than that, okay? All rolled up into a column. And so we're using this technique to separate our compounds based on boiling point. So this is kind of, here's like the picture drawing of what it looks like, and then this is a picture of actually one of the instruments, which there's a better picture of it actually in your lab manual, of the instruments that we'll use for the experiment. The actual instrument we use, these are both GCs, the one we use is this back one. But the basic process used with a gas chromatograph is we will have our samples injected at the injector, okay? It passes through the column, and then once it passes through the column, it's separated by doing that and comes out the detector and detects it, and then that information goes on to the computer and data system that then tells you what is the composition of, or what relative percentages of different things are in your sample, okay? So starting with the injector, what we do first of all is we vaporize the sample, okay? And so this is kind of a very blown up version of what our column looks like on our GC column. So like if you cut it right down the middle, this is what it looks like. You've got the outer coating, and then you've got the inner coating of the GC column. And our stationary phase is that inner liquid polymer coating, okay? So what happens is we inject our sample, which is going to be in a solution of pentane, but it's usually, it's not, you don't usually inject any sample, it's going to be in some solution, okay? The solution goes into the injector and it gets vaporized, okay? Then it comes to the column as a vapor, and that column isn't as hot as the injector, okay? But it has been vaporized. So we've got this vapor that then goes through the column that is gradually increased in temperature, and based on the boiling points of the components, the more volatile components will just speed through the column, versus the less volatile components will have more time to spend in the column and will spend more time in the column, okay? And so then eventually you get separation of all of your components, and then it goes on to the detector. A couple things with GC, the reason that we are using this is we can separate compounds with very similar boiling point ranges. So like when we're looking at our alkenes, there is not a large difference in boiling point ranges. So we can't take your alkene mixture and go on it and do a fractional distillation in lab and separate your alkene mixture based on the boiling point ranges, because we just won't separate them out. But with GC, we can. And like we always talk about with chromatography, we talk about its stationary phase and its mobile phase. So the stationary phase I've already kind of talked about, is that liquid polymer coating on the inside of the column. What carries the sample through the GC is the carrier gas, or carrier gas mixture, okay? And so our mobile phase is that carrier gas or gases that pushes it through the GC, all right? So once it goes through the column, then we have to detect the sample. And what we use for a detector is what's called an FID. It's a flame ionization detector. And this is, we use this detector because it's a very sensitive detector. So the FID comes from the F, the I, and the D, okay? So what happens, try and make this a little less blurry here. What happens is we've got our carrier gas coming into the detector, okay? Actually, sorry. We've got, this is our injector, sorry. Wrong picture. This would look better as a detector, okay? So we've got our carrier gas with our sample coming in to this detector, all right? We also have hydrogen being brought into the detector as well. And what happens is that both of these streams meet and are in the flame, and we basically are charring our sample in the presence of an electrostatic potential, okay? And what happens from that is then we get individual electrons that come off, as well as fragments of the compounds that are ionized, okay? And so then what is detected is those ionized fragments. And the detector is sensitive enough that it detects how much of each of those ionized fragments are present, okay? So it will detect them in the order that they come off, so they have to be separated out by the time they come off the column. There's no separation occurring in the detector. But once they are separated, within that detector, we basically char them and ionize them, and then detect those ionized fragments and how much of each of those ionized fragments came off of the detector, all right? And so then that's what you get that comes out of the, as your chromatogram. So what you see, let's see, let me show this one. What you will see that comes off then is different peaks in the chromatogram. These are representing the different fragments of that sample that came off of the GC. Okay? So you'll see individual peaks, and then the numbers above the peaks are the retention time. So that's the time from the point where the sample was injected that it came off the column and was detected. All right? And so these are actual units, these are time units, all right? And then you have the relative intensities. These are the response, the y-axis is just the relative response of each of these fragments, how much of it, so that the amount is determined by how large the peak is and how much area is under the peak. So that's all calculated for you, all right? So then the other part of what you get is this part that will give you a list of your peaks and the retention time that the peak came off. And then what you want to worry about is the percent of the total mixture, how much of that peak was represented in that total mixture. Okay. And we'll get in experiment 16, we'll get into looking at the peak area and recalculating things, but you shouldn't have to do a whole lot of that for experiment 8 and 11, okay? One thing you do want to do for experiment 8 and 11 is anything with a retention time, so I'm going to just say RT for retention time, of less than 2 minutes, you don't you don't want to look at that in your analysis, okay? So if you have anything less than 2 minutes, you don't want to use for your analysis. So what you want to look at as far as analyzing this data, here's a table you're going to put together, and here's all the data put together, okay? So you'll have your chromatogram, you'll have your peak table, all right? So you'll get 2 pieces of paper with each sample that you run. The chromatogram and then the peak table will be on a separate sheet of paper. What you're also going to get is from your lab professor, you will get a list of standard retention times, okay? And so that is how you're going to know what the compounds are, or at least start to identify what the compounds are, okay? And so you're going to put a table together like table 10.2, and this is in your lab manual, where you're going to list the standard retention times based on that table that you get, the experimental retention times. You want to give the area totals and then the peak area. So you'll look at those area totals, but you're not going to do a lot of calculations with them. And then you'll look at your percent area, and that should total 100%, okay? So you'll list all of those standards that pertain to your sample, and then there may be peaks that you have to identify that you don't have standards for. And so in that case, then you will propose what that peak is without having a standard retention time and a standard to say what it is, okay? So one of those is, example here, you could end up with the ketone that corresponds to your alcohol in your mixture, okay? So we talked about last week not adding your aldehyde too fast because that'll cause a lot of ketone to also form. Even if you were careful with your aldehyde addition, you can still get your alcohol to oxidize to a ketone. That's just a reaction that can happen with alcohols, okay? So those ketones have a retention time slightly smaller than your alcohol retention time. So when you get the list of the retention times, you'll have all the 4 possibilities for the alcohols. You won't have the possible ketones that could form. But if you have a peak with a slightly lower retention time than the alcohol, most likely that is the ketone that corresponds to your alcohol. So in this example, that was what was listed here, was the possible 4-heptanone from the 4-heptanol starting material, okay? There may be other impurities that you're going to have to figure out in the GC traces as well, okay, that aren't listed in the standard. So you'll have to do the best you can to identify those. You also have to be careful with your alkenes to not list things you can't identify as impurities. So when we give you the list of standard retention times, we don't have every possible alkene that all of you could have made, okay? So we're going to give you a trend in the table that shows you how positional isomers are related to each other with the retention time, and we will give you a set of standards that shows you how cis and trans isomers are related to each other, as well as position of those cis and trans isomers, okay? Then you have to use that data to then look at your data and figure out what corresponds to your data and where you have holes in your data. When you don't have peaks that match, standard retention times that match your data exactly, then that's when you have to start figuring out, okay, well, if I have this trans alkene, I don't see the cis alkene in this list of standard retention times. But that doesn't mean it doesn't exist, because we talked about for every trans alkene, you have a cis alkene. So you then have to figure out, okay, if I've got trans alkene, where is that cis alkene going to fall, okay? So there'll be situations like that where you have to figure out, based on the standards, what makes sense for your data, okay? So be really careful identifying anything as an impurity, especially in the retention time range of the alkenes, unless you're absolutely sure it's an impurity and not one of your possible alkenes, okay? All right, so another thing that you're going to need to look at this week, or at some point get into your lab manual, is the GCs are in the IR room back behind the IR, so they're in 3123. On the GC that we use for running experiment 8 and 11, and then we'll also use that same GC for experiment 14, we have this table posted on the front of the GC. Okay, so this table is in your lab manual. You need to get this table in your notebook as well, all right? And what this table shows you is basically the program for the column temperatures as we set up the method in the GC, okay? So the biggest thing that we vary when we set up different methods in the GC is the column temperatures, because the injector is always at a standard temperature. What is happening in the detector with the gas flow and the sample going in and then being ionized with the hydrogen flame also happens with a standard set of conditions. But what is varied is what happens with the column. And so what you're going to want to do is go through and fill out this table. And so there's things like, how long is the column? What is the inner diameter of the column? What is the stationary phase and the film thickness? These are all things that can vary with different types of columns. Okay? You have to give the injector temperature, the detector temperature, and then the program of the oven temperature is what changes how different compounds come off and what different retention times they have. So you'll give the initial temperature, the initial time that it stays. So what it means by time is how long does it stay at that temperature in the program. And then what is the rate of temperature increase, what is the final temperature, and how long does it stay at that final temperature within that method, okay? And then different information about the carrier gas and split ratio and so forth. And so you want to make sure that this information gets in your lab notebook, either with experiment 8 or with experiment 11, but it needs to be in one of them when we go to grade your notebook, okay? Basically in the experimental. Now the column that we use is a fairly non-polar column, so on that table will be listed the type of column that's on there. The column that we use is a fairly non-polar column, so it's not going to really change how it hangs on to different compounds based on polarity. So the way that you will see the compounds coming off of the GC for the most part is going to be based on boiling point. The separation is going to be based on boiling point. Okay? So I'm going to put, I kind of alluded to that, but I want to make sure that you understand that. That especially for our separations, the separation is based on boiling point of the different compounds that are coming off, okay? And so, based on what I talked about of volatile compounds moving through quickly versus not as volatile compounds slowing down, what's going to elute first? Higher boiling compounds or lower boiling compounds? Lower boiling compounds are going to be what comes off first. So your lower retention times are going to be the lower boiling compounds, okay? As you look at that chromatogram, as the retention times increase, that means those components have higher boiling points than what came off previously. Okay? And the way we've set up the method, you're not going to have to worry about interpreting where the solvent comes off, because we set it up so you don't see that. So that's not part of what you're trying to figure out. Okay? So this week, we will collect your samples. As we run the samples and get them back to you, we will let you know that we've returned them back to you, most likely in your cubby. Hang on to those chromatograms, because once you have the chromatograms for your sample, we're gonna have, if we have to reproduce chromatograms, we're going to have to basically go back and get new data. Okay, so hang on to what you're given, because you'll need it for your report.